Learning by doing is the best way to learn a new skill. Data science is no exception. In this video, I'm going to take you through a real-world data science project for that very reason. We'll dive into real data to uncover valuable insights about customer behavior using K-means clustering. By the end, you'll not only have gained skills in the data science process, but also learned a powerful technique to profile and understand a business's customers. Hey folks, I'm Trent. I've been a professional data engineer for 5 years, and in this video, I'm excited to take you through a comprehensive analysis of customer data using Python. We'll dive into data exploration, data cleaning, feature engineering, applying K-means clustering, and ultimately generating insights based on the outputs. We'll be working with a real-world dataset, so we'll have to deal with problems like missing data and outliers. This project is based on work that I've done for a client and was originally inspired by a white paper, which I'll link to in the description below. We'll focus on 3 key features of a client, those being recency, so how many days has it been since a client made a purchase, frequency, how many total purchases has a client made in the dataset, and monetary value, the sum total monetary contribution of each client in the dataset. This is typically referred to as RFM analysis, or recency, frequency, and monetary analysis. Why use K-means clustering? Well, it's a powerful unsupervised machine learning algorithm that helps us uncover patterns in our data. Unsupervised meaning that the algorithm does not train on known data to predict or infer on new data. It instead aims to discover patterns in existing data. To give you some intuition, you've probably come across the urgency importance matrix used in time management. You've likely seen how tasks are grouped into categories like do, delegate, remove, and plan. These groupings are based on the 2 features, urgency and importance. Similarly, K-means helps us cluster our data into meaningful groups, allowing us to derive actionable insights. Additionally, when analyzing large datasets, clustering and categorization can help us overcome overwhelm by suggesting actions, strategies, or clear next steps for further analysis. So to summarize, in our project, we'll apply K-means to customer data using the features of RFM to better understand customer behavior. Our goal is to help an online retailer better understand their customers. The dataset that we're going to use is this Online Retail 2 dataset from UC Irvine, the UC Irvine machine learning repository. I'll leave a link to this in the description as well. And it contains all the transactions occurring for a UK-based online retail store for the years of 2009 up to 2011. We are given some variable information over here about the different variables in the dataset, like the invoice number, stock code, product description, quantity of products bought, the invoice date, the unit price, customer ID, and country. So I've gone ahead and downloaded this dataset. It turns out to be an Excel spreadsheet that looks like this. We can see all of our different columns over here. And if I take a look at the count, there are about 520,000 records in this dataset, so reasonably big. It also consists of 2 different sheets, one for the year 2009 to 2010, and the other for 2010 to 2011. For our analysis, I'm just going to use the 2009 to 2010 data. Now, with that overview in mind, it's time to jump into our very first step, which is exploratory data analysis, where we'll get to know our data and determine the necessary cleaning steps to prepare the data for feature engineering. Jumping into my editor over here, I've got my project folder open. In it, I have downloaded and placed our Online Retail 2 data in a folder called Data. I've got my notebook over here, Online Retail Data Clustering. This will contain our entire project. And I have a requirements.txt file here to capture all of the different dependencies required for this project. So for this project, I will leave a link to my GitHub if you want to follow along. And if you are following along, to install these dependencies of Pandas, Matplotlib, Seaborn, Scikit-learn, and OpenPyXL, all you need to do is do a pip requirements.txt. If you hit enter, it will install all of these packages. I'm getting requirement already satisfied because I have done this step already. Just a note as to why you need OpenPyXL over here. This is required as an engine for Pandas to be able to read Excel files, and as I said, our data is stored in an Excel file. So just a little note there. All right, back in the main notebook over here, I am importing from our different packages over here. So we're going to use Pandas, Matplotlib, scikit-learn, etc. And it'll become clear where we're using each of these different imports as we go through the project, but these are the various imports that I'm going to be using. I've also got some settings over here just to make the outputs of Pandas easier to read in a notebook. So let's go ahead and run our imports. With our imports done, we can now finally start our data exploration and read in our Excel data using the pd.readExcel method over here, give it a path to our data, and specify that we only want to read the first sheet. Okay, that took a little while to read in. I think it's just because of the Excel format and the size of the data that we're dealing with, but nonetheless, we've got our data in a data frame, and we can see it is the exact data that we saw in the Excel file, no weird formatting or anything like that. All right, let's get a high-level view of what our data looks like by using df.info over here. And we can see we've got our 520,000 entries over here, or roughly 520,000 entries. Our different columns over here and their data types. And off the bat, we can see that customer ID is missing some data. It only has about 417,000 non-null values, whereas the total is in the 500s of thousands over here. So that's something we're going to have to deal with. Something great is that the invoice date has been picked up as a date time already, so we don't have to do that conversion. The rest of the data types look okay. They could be made more optimal, but I'm comfortable with the set data types over here. You can also see that the memory usage is about 32.1 megabytes. So that is kind of big, but nothing that a regular machine can't handle. To get some more high-level statistics on our data, we are going to use the df.describe over here and take a look at our numerical data. So describe by default will only look at numeric data. We'll look at the object data in a second. So something interesting to note over here is the minimum value for quantity is negative. So you wouldn't expect that, right? Because quantities you expect to be positive for a sale. So that's a little interesting over there. We can see as well that price has got a negative value in it, which is a little unexpected and suspicious. And again, a customer is missing data. It has less records or less non-null records than the rest of the columns. Well, we'll have to investigate that a little further. But in the meantime, let us do another describe, but specifically on our object data. So we can specify the keyword of include and capital O over here to get a description of our objects or string-like data. So invoice is considered a string, which is interesting. We can see their various counts over here. The unique values, so about, 28,000 unique invoices, 4,600 unique stock codes, and 4,681 unique descriptions. That's interesting. These don't align. Perhaps something to look at, but this looks good otherwise. All right, the first thing I want to deal with is taking a look at the missing customer data. So if we take our data frame and then select where our data frame column customer ID is NA over here, and then take a sample of 10 of those records. So this just filters our data for customer IDs, which are null over here. And if I run that, let's take a look at these records. So this is quite interesting. The product description over here for just the small sample, .com sales, a quantity of -100, and of course, missing customer data, and prices are 0. So these look like records that we want to exclude. And further, if we look at the rest of the records over here, even when there are legit looking transactions, when we don't have a customer, we can't categorize or effectively work on that data because it's near impossible for us to infer which customer made this purchase. So I think the strategy we're going to choose when we get to cleaning is to drop the null customers. The next interesting facet that I want to look at in this data is the negative quantities specifically, and see what that data looks like. So to do that, let's take our data frame, df, and then filter where df quantity is less than 0. So where it's negative, and let's just get a sample of like 10. Alrighty, we can see some null customers over here. We can also see that for these transactions with negative quantities, some of these invoices contain a C in there. And I think in the data description, if I remember correctly, in the data description, invoice number is a 6-digit integral number. If this starts with the letter C, it indicates a cancellation. So we can have cancellations in our data as well. So that's something interesting to note. We'll investigate that a little further. Let's actually take a look at our invoice data in a bit more detail. So to do that, and with the knowledge of our invoice numbers having these C's or cancellations in them, let's take a look at the various types of invoice numbers we can get and check if all the invoice numbers obey the standard of being 6 digits long with either no letter in front of them, no letter C, or a C in front of them. To do that, I'm going to take our data frame, invoice column, and the first thing I'm going to do is actually set this to a string, or specifically cast it as a string so that I can use regex on top of it. I'll explain that in a minute. So let's go ahead and say df invoice equals df invoice dot as type to cast it as a string over here. Let's use that. To validate our pattern of the invoice numbers, we're going to build up a regex expression. So first, I'm going to take our data frame and then filter it for where df invoice, then access the string methods with .stir for string, and then use the match method over here to do regex matching on our data. If you're unfamiliar with regex, it's just a pattern matching syntax for text data. So you can match various patterns in your data and filter your data that way. It's really handy. Can get a little complicated, but we're not going to do anything too fancy. All right, so let's enter our regex pattern. And what we want to match, a 6-digit number, right? So let's go ahead and say double backslash over here, D for digits. So in regex, D stands for digit, repeating 6 times exactly. Then to indicate that I want 6 digits and 6 digits only, I'm going to use the anchor caret symbol over here. This just says that this must be the start of our string. We can't just match 6 digits anywhere in our string. We actually want to match exactly this pattern of digits, 6 of them, and then I'm going to use the end anchor over here, which is a dollar symbol. So this specifies that we want 6 digits exactly, nothing more, nothing less. So we've given this filter expression over here, and what I want to do is say where this match is true first. Let's take a look at what that looks like. And these are our typical invoice numbers over here. And what I'm interested in actually is where these are false. So where we are not getting 6 digits exactly. And in the sample, we can see the C's or cancellations coming up. What I'm interested in though is if C is the only unique letter that appears in front of an invoice number. To validate if C is the only letter that appears in front of our invoice numbers, or is the only character that appears in our invoice number, I am going to basically scrub out all of the digits over here. So all of these digits over here, and then get the unique values that come back after taking out all of the digits to see if C is the only character that appears. So to do that, what I'm going to do is take data frame, take the invoice number, access the string methods again, and over here I'm going to do a replace. What I'm going to replace are all of the digits. So once again, I'm going to use regex syntax. So in these square brackets, I'm going to specify 0 through 9, so all digits. Then replace this with an empty character. So I'm going to replace all digits with an empty string. And we need to specify that regex is true over here. So we are in fact using regex. So this basically scrubs out all the digits, and you can see we're getting a bunch of nulls back. What I really want is a unique list of values once I've done this. So I'm going to use .unique to return the unique values. And we can see, interestingly, that we get a C over here for cancellation, but also an A, which is a little unexpected. So cancellations aren't the only invoice type that we can get apparently. There are also ones that start with A. Let's take a look at those. So to investigate, we're going to take our data frame. Once again, this time we're going to filter the whole data frame with the expression df invoice once more dot string dot starts with. So I want to see if the invoice numbers start with an A or what those invoices are about. So starts with the character A over here. And these are the invoice numbers we get. It looks like we only get 3 values over here, so not a very big subset of the data, but these look like accounting type of transactions over here. So adjust bad debt for negative 389,000, like 389,025 pounds, which is a lot of money. So lots of bad debt apparently, but there are only 3 records over here, so I'm not too worried about this. However, I'm going to remove these nonetheless when we get to cleaning. We don't actually want to use these in our analyses. It doesn't look like these apply to any valid customers. These look like pure accounting types of transactions. Okay, the next interesting column that I want to inspect is the stock code column. So we have some rules that were specified in our description of the data over here for the stock code, basically saying that it is a 5-digit integral number uniquely assigned to each distinct product. I want to test if this is true for all of our cases. So I want to test that stock code only consists of 5-digit numbers. Once again, I'm going to use regex for this. So let us go ahead and first cast our stock code as a string, just to be certain that it is of a string type and we can actually apply regex to it. So we'll specify df.stockcode or df stock code equals df stock code once more dot as type string here. To examine our stock codes, I'm going to use a specific regex pattern to check if we get 5 digits recurring. So to do that, I'm going to say df where df stock code dot string dot match, and then specify a regex pattern for 5 digits. So in here, we are going to specify \d for digit, say 5 digits repeating. And I want to anchor this, so to make this specifically 5 digits and 5 digits only, I'm going to use the caret and $ anchors again. And I actually want to look at where this is false. So where any records disobey this pattern that we expect of the stock code, and see if we get examples of that. So let's go ahead and run this. And we can see that the stock code actually contains letters at the end of it. So these look like legit transactions though. We actually do get a customer ID over here, and I'm not sure what the letters at the end over here indicate, but these look like legit transactions. And nothing's mentioned in the data documentation. So unfortunately, we have to assume that these are valid, and I'm going to make that assumption and be okay with these transactions. To be comprehensive on the stock codes, I want to test if I get any other results besides these 5 digits followed by letters at the end, to see if there are any other unique stock codes that we should be aware of for our analysis. To do that, I'm going to use a more complex statement to filter our data. So let us take this first statement, which I'm happy with because this is our first set of transactions or stock codes that we believe are legit. And I want to add a compound statement, so I'm going to use the ampersand symbol over here to indicate and. So that is a logical and. I'm going to use a very similar syntax, so I'm just going to copy and paste this over here. All right, so this is the exact same statement, but I want to add in over here that I'm okay with letters being at the end of the statement. So to capture that in regex, we use the syntax of the square brackets, A through to Z in lowercase, and then capital A through to capital Z in uppercase. And I'm okay if the letters repeat. that's what the plus sign indicates over here as well. So I'm okay with 5 digits followed by repeating letters as well. Now I want to see where this is false, so it does not match this pattern, and also it does not match this pattern either. So let's go ahead and run this and see if we get results. And as it turns out, we do get some funky looking stock codes over here. So we've got this dot over here for .com postage, an M for manual, D for discount, and a post for postage apparently. So it looks like we got a lot of stock codes that do not follow our pattern, and uniquely it looks like some of them have null customers and some of them do have customers over here. All right, so let's go ahead and take a look at the unique values we get back from the stock code, just to see the extent to which our stock codes don't follow our expected patterns. So let's go ahead and say unique over here at the end. This should work. Unique. Ooh, data frame has no attribute unique. We have to select the column. So specifically, I want the unique values from stock code. So after that super long statement, we can get a distinct list of the different stock codes that do not follow our expected patterns. Now, to deal with this, unfortunately, I think we're going to have to go through every single one of these to examine what the records mean. Through the magic of editing, I will spare you the pain of me going through all of these over here and just take you through one example and then show you the results. To systematically go through each of these, what I'm going to do is use a pattern like df, where df stock code, say stock code dot string dot contains over here. So the contains method is also a pattern matching method, but it is looking for patterns contained within our string. So string dot contains over here, then specify the caret symbol as the start anchor. And the first one I'm going to observe over here is the dot over here. So I'm going to take a look at examples where we have this dot item and just examine these records at a high level to see if they are records that we want to include. Of course, for dot over here, it looks like they almost exclusively have null customers, and also I'm not interested in postage fees, which these seem to be. To complete this analysis over here, I'm going to go through each and every one of these, but I will spare you that pain and just give you the results. All right, so systematically going through each and every single one of those weird stock codes, I came up with a section over here called notes, where I'm just taking note of the stock code observations that we've made. And over here, I've tabulated each of the patterns that we saw. And it turns out that majority of them we would actually want to exclude from our clustering later on. So we want to reject these during data cleaning. And the only one that looks like legit transactions are the ones that contain the stock code of pads over here. So look like legit stock codes for padding, like actual products that are pads. And so I'm going to include those, but the rest, yeah, we're going to reject these during cleaning. Now, for completeness' sake, we could go ahead and observe the values in description as well as in country, for example, but we're not really interested in those for our clustering exercise. So I'm not going to do the exploratory data analysis of those in this video, but for completeness' sake, we could go through each of the descriptions, like look at the different types of descriptions we get using regex again. And we could also look at country to see if we get valid countries back, but we're not really going to use those for our analysis. I'm going to skip over that and move right along to data cleaning so we can prepare for our feature engineering step. Alrighty, now that we've got our exploratory data analysis done, we're going to move on to data cleaning using the insights that we've gotten from our EDA. To start cleaning, I'm going to create a new data frame called cleaned.df and make this a copy of our original data frame over here. And the first column that I want to clean is the invoice column. So let's take clean.df. And again, make sure that this is cast to a string. We're doing this so that we can apply rejects to this because we know that there are specific invoice patterns that we want to filter out, those being the cancellations and those accounting invoice patterns with the A in the front of them. So let us take cleandf invoice dot as type string over here. And what I'm going to do is create a new variable called mask. This is typically used as a pattern for filtering in Pandas. So a mask is just a filter expression that you can use in your data frame. So let us create a mask over here. And to make it easy to read, I'm going to add some brackets and then specify in here that cleandf should follow a pattern. So string.match should follow our pattern that we expect. So we're going to use the caret anchor again, little backslash digits, so 6 digits reoccurring, and the end anchor. So our invoice should be exactly 6 digits, nothing more, nothing less. And we want this match to be true in this case. All right, so only invoices that follow this exact pattern. And to achieve the filtering, we're going to take cleandf over here and specify cleandf equals cleandf where cleandf follows this mask over here. Alrighty, so let's run this and see that we get a good output. All right, so we have now filtered out all of the invoices which do not match this pattern. So similarly, I'm going to do this type of exercise for the stock codes as well. Now, stock codes are a little more complex because the patterns were a little more complex. But similar idea over here, we are once again going to cast our stock codes this time as a string, or make sure that they are of the string type stock code, and then develop a mask over here. Our mask should look something like the following. So to take you through the mask that is here for stock code, we want matches of 5 digits, so where we get exactly 5 digits for our stock code, or, so this pipe symbol over here means or, and we want stock codes that are 5 digits long or are 5 digits long and are followed by letters over here. And then finally, that one stock code that I found that looks legit is this pads stock code over here. So any of these matches that are true, we want to include those in our cleaned data set. So again, we are going to take cleandf and set it equal to cleandf with the mask applied to it. And just to make sure we get a good output, let's run that. Okay, things look good. And we still have a significant amount of data. Alrighty, so we've dealt with invoices and stock codes. What I'm hoping is that our price data will automatically be fixed. So remember, we had negative prices and negative quantities. By removing these kind of weird transactions from the invoices and stock codes, I'm hoping that that's automatically corrected our data. So I'm going to take cleandf.describe over here. So looking at the output of our describe on our current cleaned df, we can see that quantity is still got negative values and price now has a minimum value of 0. So we're still going to have to deal with that. And I realize now that we forgot to deal with our null customers, right? So I need to go ahead and drop these null customer IDs first. Let's do that first and then go ahead and relook at our statistics. So let us grab our cleaned df.drop NA. So we want to drop nulls and then specify a subset. So subset will specify a subset of columns to actually perform the drop null on. And the only column we want to do this on really is customer ID over here. And let's do this in place. So in place specifies that we are going to do this operation on the current data frame over here. We don't have to reassign it. That's all that in place specifies. So let's run that. All right, yeah, this is just upset that I'm doing this on a copy. That's okay. And let's go ahead and look at our describe now. And we've dealt with our quantity problem, it seems. Our minimum value for quantity is 1, so getting rid of the null customers has helped us resolve the weird quantities issue, because a lot of those negative quantities seemed to have null customers attached to them. Yet our price is still got a 0 on it, and I don't really want to include 0 prices, but let's just go ahead and look at what our 0 prices actually mean. So cleaned df over here and specify price is equal to 0. Let's take a look at these records. Okay, so I don't fully understand these records as to why price is 0 in this case. Maybe the person got a free item or something like that. But if that's the case, I don't really want to include this in our analysis. So let's take a look at the length of this guy. And it seems to only be 28 records, so I don't really feel bad about filtering these out. It's a very small sample set, and I don't think 0 priced items should be included in our customer analysis. So let us deal with that by adding another code block over here. We can say cleaned df equals cleaned df is greater than 0. Here. Let's run that and do a describe once more. So this is really weird. My minimum is 0.00. It might just be a really small number, but that's really strange. I wonder what's going on there. Well, let's actually take a look at what our cleaned df minimum is for price. So cleaned. Okay, it looks like we've got a really small price over here of 0.01. It seems like this is not being printed out actually because of the settings I set earlier. That's okay, so long as it is greater than 0, I'm happy with that. That is a little weird over here to see, but it turns out that we do have all prices greater than 0 in our data. And even if I look at this again, looking at the length of the clean df where price equals 0, I do get a 0 value back. So that's good. To finish things off on our cleaning or data cleaning, a good metric to keep track of is how much data you have dropped or lost due to your cleaning steps. This is often asked for by clients or by teams that you're working with, like how much data did you lose during your cleaning process? So it's good practice to actually take note of that. So to do that, all I'm going to do is take the length of our clean df, so how many records we have in the clean data frame, and the length of the original data frame over here. Take a look. So it seems like we've still got about 77% of our data, meaning that we lost about 23% of our data during cleaning. And we can note this in Markdown. We can just add a Markdown block over here. We can say dropped 23% of records. Before we move on to feature engineering, I want to go into a bit of the theory around how K-means clustering actually works. I think this is important to note or to understand a little bit of how the algorithm actually works before we dive into feature engineering, because a lot of this context will inform the feature engineering decisions that we make. So I'm just going to walk you through a visual explanation of how the K-means clustering algorithm works. So starting off, we can plot a random set of data over here. So this is just randomly generated data on 2 dimensions over here. So we've got 2 separate dimensions and a scatter plot of our data in black over here, all these black dots. And the first thing we're going to initialize are random centroids. It'll become clear what a centroid is in a minute, but effectively we just initialize some random points which are marked by these red X's over here. Then what we're going to do is an initial classification. With these completely random points, we classify our data based on how close they are to the different points. So in this case, we've selected 3 different centroids or centers to use for our clusters, basically assuming that we have 3 separate clusters in our data. We classify the data in this next panel to one to the right over here, where each data point that is closest to a specific centroid is given a different color. So here are our 3 initial clusters classified. After we've done this initial classification, we now recompute a centroid, which is just an average of the cluster of points, a vector average on the cluster of points. So effectively, if we look at the purple cluster over here, what we want to do is compute the average vector in this cluster that we've just formed. So when we work out that average in this cluster, we will then determine a new centroid. We'll repeat this for each of the different centroids, basically working out a new average. So if I move on to this next panel over here, you can see I've marked the old centroids, our original centroids from this panel, in gray over here, and the new centroids as red X's. So now that we've moved the centroids over, we reclassify our data based on the same principle, basically which point is closest to the centroid. So you can see that a couple of these purple points over here have been reclassified as turquoise with the new centroids. This effect is more pronounced on the yellow cluster over here. You can see some of these points were yellow previously, but when we recomputed the new centroids, these became part of the purple cluster. Then continuing on, we repeat the exact same steps. We take a look at our clusters, we recompute the centroids, and then reclassify our data. So if I scroll down to this next iteration over here, you can see that this cluster, the turquoise cluster, didn't move very much, so it seems to be getting stable. But the purple cluster's centroid moved down a little, and the yellow cluster centroid moved to the left a little more over here. So after recomputing these averages, we reclassify our data. So we can see that the purple cluster compared to this panel over here has now gotten some more points. And we repeat again, recompute the centroids, right? So again, they're marked in gray over here, the old centroids compared to the new centroids. And you can see they're moving a little less on this third iteration over here. And we reclassify our data after recomputing them, and then move on to another iteration. And you can see, funnily enough, that our turquoise cluster is now getting shifted. So is our purple cluster, but the yellow cluster seems to be stable. And effectively, this process repeats until we reach a point of stability, ideally when the centroids stop moving. But in the real world, with real data, you don't always reach 0, or you almost never reach a 0 point or 0 movement in your centroids. You just kind of accept a minimum. But we will go through that when we actually do our K-means clustering. However, again, I think it's just important that we understand a little bit about the K-means clustering algorithm, because it will inform a lot of our feature engineering decisions. With some theory behind us and a clean data set, it's time for us to move on to our feature engineering step. So these features will help us get a new perspective on our data. And to recap, the features that we want to use to analyze our customers are the features of recency, so how many days has it been since their last purchase, frequency, how many times have they made a purchase, and monetary value, or the sum total monetary amount that a particular customer has spent. The first step that I want to follow is actually to compute a line total, or a total amount spent on a particular transaction line, so that we can easily aggregate that into a sum of monetary values. So what I really mean by that is I'm going to take the clean df. It would help if my block was in Python, since that is what we are using. If we take our cleaned df over here and create a new column, let's call it sales line total over here. Take our columns of firstly quantity. So let's say quantity, our price over here. And let's just print out that result. Okay, let's scroll to the side. And the resulting column, sales line total, is simply the total amount per transaction line over here. So this is clear in this example. We've got a quantity of 3, a price of 3.25. So our sales line total is 9.75. As a note, I don't think I mentioned it earlier, but these sales are in pounds sterling, so not dollars or anything like that. these are in British pounds. So this is a line total of 9.75 pounds. Okay, with our total, we are now going to aggregate our data. So aggregate by grouping by our customer ID, because we want a unique set of customer IDs, and then computing the aggregates for the recency value, the frequency value, and the monetary value. I'll take you through that. So let us create a new data frame called aggregated df. And this is going to be equal to our cleandf.groupBy over here. And we want to group by our customer ID. Now in the group by method, I will set this as index parameter to false, because I don't want to use my customer IDs necessarily as my index for my resulting data frame. So I'm going to set that as false. Then to keep this looking somewhat neat, I'm just going to use this backslash character over here to basically do a run on line. This is just some Pandas syntax that lets me continue my line, this line of code on a new line over here. So now I'm going to do a .ag for aggregate. And in the aggregate method, I'm going to specify the new column names for my aggregates. So the first one is going to be monetary value over here. So that's the new column name. And this is equal to taking sales line total over here and aggregating it via a sum. So this is the syntax we use for an aggregate. We specify a new column name equals the original column name and the aggregation we want to perform. All right, so that's for the monetary value. Now for frequency, which is another column that we want to create, or aggregate that we want to create, we want to take the invoice numbers. So remembering that in our data, we have different invoices, but each transaction or each line in this data frame, or it could be part of a single invoice. So you can actually see this in the first example. This 538171 is repeated. So these are different line items on a single invoice. And what we're interested in is how many invoices or unique invoices a customer has gotten in the period of the data set. So to do that, the aggregate we want to use is this unique aggregate over here, and that stands for number of unique values of invoices, and that should determine our frequency. All right, and then lastly, I'm actually going to create a column called last invoice date, which is going to be our invoice date, and we want to take a maximum. And we're going to use this to determine our recency in the next step. But for now, let's take a look at the result we get. So aggregated df, and let's just take a small sample, and we get our different customer IDs over here. So unique customer IDs, 12346, 12347. There's some total monetary value in the data set. So this customer has in total spent £169. And this was spread over 2 different transactions or 2 different invoices. And the last invoice date over here was the 28th of June in 2010. We can even see down to the time was about 2 o'clock. All right, now we need to get our recency feature. And to do that, I'm going to leverage our last invoice date over here. So to start this off, I'm going to use a max invoice date over here, and this will equal my aggregated data frame. And let's take our last invoice date dot max. Okay, so this is going to be our very last invoice date. I actually wanted to print that out to see what it was. Okay, so this is the 9th of December in 2010, and I'm going to use this date to base my recency off of. Now, in a real analysis, you may want to use today's date to determine your recency, but that's a little weird because this data is really old, right? So we're going to get huge numbers for our recency, but for the purposes of this project, I'm just going to assume that the max invoice date will help us determine recency, or make that assumption over there. But IRL, you'll want to use something like the current date stamp. Okay, so let us take our aggregated data frame and create a new column called recency. And recency is equal to the max invoice date, the column of the last invoice date over here. And I want this specifically in days. So I want my recency to be measured in days. We could use hours, but I'm going to use days. It's just simpler to interpret. But to do that, I'm now going to use the .dt for datetime methods in Pandas. So .dt.days. And if I go ahead and print this data frame out, let's just look at the top 5 records. If I print this out, we can see we've got a recency of 164 days for this record. So lost, or how long it's been since the person's last transaction relative to the maximum date in our dataset, or maximum invoice date in our dataset, it has been 164 days. With our shiny new features of recency, frequency, and monetary value, I now want to observe them and specifically look at the distributions of these features. Why I'm doing this is to see if we have outliers in our dataset. Going back to our theory, you can imagine how outliers could really badly influence our clustering algorithm. Your centroids may struggle to even find the outliers. If you randomly initialized a particular centroid, it may never actually find that outlier cluster, and we never reach a stability point. So it's important for us to take note of outliers in our dataset and observe if we have any. To look at our distributions, I'm just going to use histograms to plot out our different features. The code that I've added for plotting over here is using matplotlib. So I am specifying a figure. I'm going to make it quite big, a fig size of 15 and 5. That's just a ratio of the size. And I'm going to create subplots over here, right? So I'm creating a subplot grid of one row by 3 columns, and this will be the first one, this will be the second one, and this will be the third one. And in each case, I'm just repeating the process of creating a histogram, plt.hist for histogram, and then specifying the feature I want to plot with 10 bins, a unique color so that we can differentiate between them easily, and an edge color of black to make it easier to see our frequency distribution. I'm also giving them a title, an X label, and a Y label. So I've just repeated this for monetary value, frequency, and recency. All right, and then I'm just going to show this out and use the type layout function over here just to get a nice picture in the Jupyter notebook. Alrighty, there we go. So this is kind of small. Let's go ahead and zoom into this. Okay, and that is way too big. But we can see our distributions over here are really skewed for monetary value. So almost all of our data falls into this single bin over here, but we have some outlier data leaning out towards the side over here. Similarly with frequency, almost all of our data sits in this first bin, and then we have some outliers in the range of like 100. And then lastly, recency actually looks pretty decent. This distribution looks quite reasonable. This actually looks like a Poisson distribution. That's fun to say, Poisson. And the distribution looks good, right? No real outliers over here. To be rigorous about our outlier detection, I am actually going to use a box plot, and that is a feature of Seaborn, or a plot available in the Seaborn library for us to observe our data in a little more detail. The code that I've added is very similar to our frequency distribution or our histogram plots that we had prior, but in this case I'm now using SNS or Seaborn to plot out a box plot on our different features over here using the same colors as before per feature. I'm also putting this on a single plot, so I'm using subplots, just giving them a title and an X label. Let's go ahead and run this. We can see that our box plots for monetary value is super squashed, right? So the actual, or how a good box plot should look, can actually be observed in the recency feature over here. And if you are unfamiliar with a box plot, I'll just give a brief explanation of how to interpret one of these. Effectively, the box in the box plot represents your 25th and 75th percentile of your data with the median in between. So this bottom line over here represents the 25th percentile. So 25% of our data happens at or before this point. Then this middle line over here is our 50th percentile. So 50% of our data happens at or below this point. And this is also known as the median. So this is the exact median value. Then up here is the 75th percentile. So again, 75% of our data occurs at or below this point. Then these lines out here, so outside of the box plot, are a little more nuanced. Effectively, they are the interquartile range, so the difference between the 75th percentile and the 25th percentile multiplied by 1.5, so that sounds a bit arbitrary, but yep, 1.5 times this range over here, and added to the value over here. So this is the range over here, so the quartile range being added up here, and the quartile range being subtracted over here. So with that 1.5 multiplier. Effectively, this is just a way for us to gauge where our data sits and if there's any skew in the data. And typically, when data falls outside of this end gray line at the top or the gray line at the bottom, we consider those outliers. Now, for recency, there are a few outliers, actually, according to the strict definition of outlier or the interquartile range definition of an outlier. But for frequency and monetary value, we can see that the outliers are extreme, right? Because almost all of our data is squashed at the bottom over here for monetary value and squashed at the bottom over here for frequency. And we have a whole bunch of points that are so extreme, we can't even see the values in the monetary value and frequency value. So we are going to have to deal with these outlier values. Now, you may be tempted to remove these outliers or simply reject them, but the problem is that the values themselves are important, right? Because these represent customers that have spent a lot and spent really frequently. So these are important for our analysis to really help our client out in understanding their customers. And we don't want to reject these customers from our analysis because they are the most valuable customers, actually. So we have to avoid the temptation to simply drop our outliers for the sake of our model and really remember the point of our analysis. The strategy that I'm going to apply is to separate out the outliers for separate analysis or separate categorization, and then use the remaining data for our K-means clustering. So to get rid of our outliers, the first thing we want to establish is our quartile range. So we are going to use the interquartile range method to get rid of the outlier data, or at least separate out the outlier data. So let's start off with the monetary value. I'm going to declare a new variable called m_q1 over here for quartile 1. Take the aggregated data frame and then specify monetary value. And I want a quantile, right? So this method quantile will then give me the specific quantile that I seek. And in this case, I'm looking for the 25th quantile over here, or 0.25 quantile, i.e. the 25th percentile in the data. So if I print that out, you can actually see that MQ1 over here, this is the value of 307, about 307 pounds. All right, now similarly, I'm going to apply the same logic to work out 75th percentile. So this is quartile 3 over here, and this happens to be the 75th percentile. So just to distinguish the terminology being used here, this is Q1 for quartile. This is just if you split your data into quarters, right, and want to represent it that way. And we're also referring to percentiles, which can be a bit confusing, but the 25th percentile is the first quartile, and the 75th percentile is the third quartile. Of course, 100% would be the fourth quartile, right? Just for clarity's sake over there. A little confusing, I know, but hopefully that explanation suffices. Cool. So we now want to get an interquartile range, and that is just the difference between MQ3, so our monetary value quartile 3 minus M underscore Q1, and that is our interquartile range. Now, to get rid of outliers, we are going to, separate out our outliers. To separate out our outliers, we are now going to take or create a new data frame. Let's say monetary outliers is equal to, let's take our aggregated data frame. And now we want all the data that falls in between 1.5 times the interquartile range. And that is like the generally accepted definition of an outlier. There are other definitions out there, especially when you're dealing with normal data, but generally when you're talking about outliers, it is the interquartile range multiplied by 1.5 and then added to your different quartiles. So let's make that a little more clear. To get a hold or filter our data, what we want to do is take firstly our aggregated DF in monetary value, and this first part of the statement, let's deal with the data that is greater than our interquartile range multiplied by 1.5. So we actually want the third quartile, so MQ3, and then add 1.5 times our MIQR, or interquartile range. So these are going to be the outliers at the top over here. And just to be rigorous, I don't think there are any outliers at the bottom, right? Because all of our data is sitting there. But just to be rigorous and to show you how you would filter for outliers, let's do the bottom range as well. So this is the top range. So I want to add an OR statement over here, OR, and repeat aggregated DF monetary value is less than the, let's take the first quartile over here, first quartile minus 1.5 times our interquartile range over there. Okay, and then let's take this entire data frame and make a copy of it. So this will become a copy of our aggregated data frame so that this is a distinct data frame over here. And let's go ahead and run this. And actually, before I run it, let's take monetary values.describe to get our, a high-level view of what these outliers look like. Okay, we can see that there are 423 outliers over here, so reasonably big, but comparatively to our full set of data, not that big. And the minimum value over here is 3,800 pounds, and the maximum value is like 350,000 pounds. So no wonder there was a big gap over here. Cool. So happy with that. I'm just going to repeat this process once again for the frequency values because we want to get rid of outliers in frequency as well. This is pretty much a copy of our monetary outlier code, but now I am specifying frequency instead because I want to get the frequency outliers as well. So very, very similar, just specifying frequency instead of monetary value. And if I run this, which I have done already, we can take a look at the description of our frequency outliers. So in this case, there are about 279 values in the outliers over here, and the minimum frequency is 12, funnily enough, in the outlier set, and the maximum is 183. So someone who has done 183 invoices with this online retailer. Now, the frequency outliers DF and monetary outliers DF probably have overlap, right? Because some of the monetary value outliers are also frequency outliers. And that kind of makes intuitive sense, right? Because if someone's buying really frequently, they're probably spending a lot by proxy, right? So we just need to take a note of that, and that'll become important when we do our outlier analysis or categorize our outlier values. We actually have like 3 separate values that or three separate categories that we can determine: the pure monetary outliers, so high spenders; the pure frequency outliers, so the highly frequent spenders; and then those that spend a lot, so monetary outliers, who are also frequency outliers, so spend a lot and spend frequently. So we almost already have clusters available to us, but we'll come back to the outlier analysis. For now, what I want to do is get a hold of our non-outlier data, because that is what we are going to apply our K-means clustering to. What I'm going to do is create a new data frame called non-outliers df, and effectively filter our aggregated data for the values which are not outliers. To do that, I am going to use a complex filtering statement again and say, firstly, I'm going to use the not symbol over here. So this tilde means not, or the kind of negative negation operator. And I'm going to specify aggregated df. So not aggregated df, actually I'm going to say index dot is in monetary outliers df dot index. So over here, I'm leveraging the pandas indexes. So I'm saying that I want the aggregated df records where the index values are not those that are in the monetary outliers data frames index over here. So filtering out the monetary outliers. And similarly, I'm going to say and over here, and again, not aggregated df dot index dot is in the frequency value outliers df. All right, and let's print this out, or get a describe at least on this data. So non-outliers df dot describe. I made a small correction over here and added in the dot index. I forgot that previously, but basically same idea as what we did with the monetary outliers over here. We want to get rid of indexes that appear in the frequency outliers as well. So now that we've got not outliers from the monetary side and not outliers from the frequency side of things, we now print out a describe, and we can see that our values look a little better over here. So for example, the mean of the monetary value is about 885 pounds, and the standard deviation is about 817. So still a bit of variability in our data, but a lot better than we had. And similarly in frequency, we can see that we've got about 2.86, so about 3 as the average frequency, and a standard deviation of about 2.2. So also a bit of variability, but nothing too serious. What I'm going to do to validate our outlier separation is just replot our box plots, but this time using the non-outliers data frame. So this is really similar code to what we had before. This is just a box plot on our non-outliers data frame. So running this, we can see that our different features now look a lot better in terms of outliers. There are still outliers even now that we've rescaled the data, right? So still by the strict definition, we have outliers, but that is okay. This is a lot more tolerable than what we had before, where all of our data was squashed to the bottom of our box plot. So happy with this and happy to proceed. I wanted to take a quick pause from our project just to say thank you so much for watching, and ask if you are finding this content valuable, if you would consider leaving a like and subscribing to the channel. It would really help me out. I'm looking to grow this channel, and your support would really mean a lot to me. Anyway, let's get back to the actual video. Now what I want to do is actually create a plot of our data in 3 dimensions across recency, frequency, and monetary value, so that we can take a look at what the data really looks like. To do that, we are just going to start off in the typical way. So plt.figure, so create a new figure. Let's make that about 8 by 8 in size. And then let's create a new axis on our figure and say fig.add subplot. Add a subplot over here, and then specify a projection. Projection equals 3D, so this will be used for 3D plotting, and we're going to make it a scatter plot of our three different features against one another. So let's say scatter equals ax.scatter, then specify non-outliers df, firstly the monetary value, the frequency value, and lastly the recency value as well. That's our scatter plot. Then we can add some labels. In this case, we have got 3 dimensions. So we have an X label, Y label, and a Z label, or Z label, however you want to say that. So we've got our 3 different labels, and let's give this a nice title. All right, we have got a set title, 3D scatter plot of customer data, and let us plt.show. So running that, we get a pretty decent 3D plot over here of our different features. Fortunately, recency is being cut off on the side there. That's okay. We can live with that. So we can see our data in 3 dimensions here. And the first thing to notice is the different scales, right? I know that sounds obvious, but all of these features are on different scales. So our monetary value over here is of the order of thousands, frequency is of the order of tens, and then recency is of the order of hundreds. Now, Matplotlib has already scaled our data for us so that the visual looks nice. But the problem is, if we were to put these on the same scale, you can imagine that if I were to use thousands for frequency and recency, all our data would be squashed into like this corner over here and things wouldn't be that clear. Now, I mention this because our K-means algorithm is really sensitive to this kind of scaling, right? As you can imagine, the centroids that get created would be shifted dramatically in the direction of monetary value, so that would have a high influence on our centroid positioning as opposed to frequency and recency. And we don't want that. We want our algorithm to treat each of our features with equal weight or equal importance so that we get a kind of fair clustering, right? We don't want something like monetary value to be overemphasized in this analysis. And this is where scaling comes in. So if you haven't come across scaling, it's just a method or set of methods actually to go ahead and deal with the exact problem we described, the fact that our features are on different scales. So what I've got over here is just some theory to describe the type of scaling we are going to use. There are different types of scaling that you can use. In this case, I'm going to use standard scaling. So just to go through it, standard scaling transforms the features you have to have a mean of 0 and standard deviation of 1, ensuring that each feature contributes equally to the analysis. So to work this out, this is typically referred to as a z-score, but to rescale our data, what we're going to do is take our data point, x, so for every one of these data points, we are then going to remove the mean value and divide by the standard deviation across the different features. So we're going to treat each feature in isolation. So monetary value will go through this process, frequency will go through this process, and recency will go through this process. And this should put our data on more reasonable scales. Now, as a caveat, this assumes that your data is normally distributed, and that's not necessarily true for our features, but it's a fair enough assumption. We can say our data is approximately normally distributed, but just a caveat there, if you are dealing with data that really deviates from a normal distribution, this may not be the best method for you to use. As I say, there are other methods of scaling out there. All right, now to scale, we finally get to use scikit-learn. And what we're going to do is define a variable called scalar and set this equal to the standard scalar. So way in the beginning of the project, I imported this already. So be sure you have that imported if you are following along. And I am just going to assign the scalar over here to the standard scalar package or standard scalar class from scikit-learn. All right, and to use it is pretty straightforward. What we're going to do is create a new variable called scaled data equals scalar dot underscore transform, so fit and transform our data, and take our non-outliers data frame and select specifically our features. So let's do those in, let's stick with the original order we had them in. So monetary value over there, and then lastly recency. as well. And let's print what we get out. So in this case, we've gotten a NumPy array back. So this is a little quirk of the scikit-learn package. Even when I give it data frames as input, it will output NumPy arrays. So to deal with that and to make our data a little easier to deal with, I'm just going to convert this array, this multi-dimensional array, back into a data frame. And to do that, I will create a new variable called scaled data df pd.dataframe and hand it the scaled data. And importantly, I'm going to set its index to the original index we had. We have been using the indices like we did earlier for our outlier analysis, so it's important for us to keep track of the same indices. And because our data is in the same order, we can just kind of slap the indices back onto our data. All right, so this is going to be our non-outliers df.index, so use the original index. And our column names are going to be equal to monetary values, so monetary value over there, monetary value, and recency. All right, nice. Let's print this out to see what we get. And there you have it. We have a data frame and our values are scaled. So we can immediately observe that our values are a lot lower, right, for monetary value. We even have negative values, which is not a problem, but just something to note. And what I want to do is just replot our 3D plot to show you that we've maintained the shape of our data, but the scales are now different. Using the exact same code as before for our 3D plot, but now specifying scaled data df as the data that we want to plot. I will now run this and show you that our shape of the data has not changed at all, but clearly the scales have changed. And it is clear that our monetary value, frequency, and recency over here are now on comparable scales. They vary from about -1 to about 3 in each case. Great, so we have now scaled our data and are ready to move on to our K-means clustering. All right, it's a new day. I decided to take a break because it was getting late and I thought I'd start fresh to do our K-means clustering. All right, let's jump back into it. So now we want to start putting together our K-means clusters. And the important thing to note is the K in K-means. This is a free parameter determining how many clusters we need to use. So to determine how many clusters we should assign to our data, we are going to use a technique called the elbow method to determine how many clusters are appropriate. Now, just to refer back to our theory quickly, the number of clusters is determined by the number of centroids we have. And to determine the appropriate number of centroids, we want to find a point where these centers are stable. So you can see in the beginning, or just as a reminder in the beginning, these centers were pretty unstable and moving around a lot. We want to reach a point where they don't move around a lot, and it has come to a point where the average distance from the points in the cluster is minimized, right, or are minimized. And this distance is known as the inertia, or is commonly referred to as the inertia. It's just the vector distance, or the average vector distance between these points and the appropriate center allocated to the cluster. So to find that, what we're going to do is try a whole bunch of different values of k and see what the inertia is for each of those values of k to determine what the appropriate value of k is. So let's go ahead and do that. The first thing we want to do is add an upper limit to how many clusters we want to test out. So I'll call this max k and I'll assign it 12 for now. Then I'm going to create a new list called inertia, just an empty list to save all of our different inertia values for every iteration where we try a different value of k. Then I'm going to create a list of k values. So let's go ahead and create k values equals range, and we're going to start from 2 up until max k plus 1. So we're starting from 2 because one cluster doesn't make a lot of sense. That would just be our data as a whole. And The max k over here, I'm adding 1 to it because the range keyword only goes up to 1 minus the maximum here. So it is exclusive of the maximum we specify, and that's why I'm adding 1 here. So we'll get a range from 2 to 12 over here. Then I'm going to iterate for k in k values, so iterating through each of our k values. I'm then going to create a new KMeans model, which I'll call KMeans, and then use the KMeans class from scikit-learn. Then I'll specify the keyword in clusters, which is our k value equals k. I will set a random state equal to 42. You can choose any number here, but basically a random state just means that you will get repeatable results. Remember that your initial assignment of centroids is random, and so we want this to be repeatable and somewhat fair, so it's just common practice to set your random state to a fixed number. Then there's the keyword of max iter, which by default I believe is 300. Yeah, max iter's default is 300. I'm going to set this to 1000. This is just how many iterations we go through before we stop the process of moving the centroids of our cluster. Right, now that we've got our KMeans model, what we want to do is take the inertia of our KMeans model. So the first thing we have to do is actually fit our KMeans cluster to our data. So we're going to take our variable KMeans, KMeans.fit and predict. So we're going to fit it to the data and predict on the data all in one go over here. The data we want to predict on is our scale data. So I'm going to take scale data df over here. Now we want to take the inertia value of our KMeans cluster for each iteration. So I'm just going to take our list inertia and append to it the inertia value of our KMeans model for each iteration. So .kmeans.inertia underscore over here. And this will save that average distance between the cluster centers and the data points in each cluster. Now I'm just going to plot the inertia values by first specifying a PLT or a matplotlib.figure. Let's make this pretty big. Let's say fig size equals something like 14 by 6, and then use plt.plot our k values. So this will be the entire range of values from 2 to 12 against our inertia values. So our list of inertia values for each iteration. I'm going to give this a marker that is a circle over here. So marker equals circle, and then just add a title, X labels and Y labels as well. So I've just added our metadata over here, and the last thing I want to do is just plt.show. I've also just added a grid over here. This plt.grid just means that there's a grid on our figure. This just makes it a little easier to read. So let's go ahead and run this. Okay, that was pretty quick. And you can see over here, we have plotted out the various inertia values. So the average distance between the cluster centers and the data points. And on the x-axis over here, we have the various numbers of clusters that we tried per iteration. So the inertia value starts off pretty high and slowly lowers down. Well, first it rapidly lowers and then slows down over here. And the technique of the elbow method is determining the point at which you see the elbow of the curve. And in my mind, it looks like between 4 and 5 clusters over here, we get a kind of stability in how many clusters we should allocate. We're not really getting much more performance by adding clusters over here. Really, our maximum benefit comes from allocating about 4 or 5 clusters. Now, to really decide between the 4 and 5 clusters, I'm actually going to use another metric to help us out and make our decision, and this is called the silhouette score. Just to give you a definition of the silhouette score, it looks something like this. Effectively, the silhouette score is the difference on the numerator over here between the minimum average distance between I and all points in the nearest cluster. So I is just a random data point, or we do this for each and every data point. So the minimum average distance between it and all points in the nearest cluster to which I does not belong. And A of the data point I is the average distance between I and all other points in the same cluster. So effectively, the way to interpret this is a high silhouette score will tell you that there is not a lot of overlap between your clusters. It's called a silhouette because you can kind of think of the clusters overshadowing one another. So a higher score is good and a lower score means that there is a lot of overlap. Just from this equation, the score will range between -1 and 1. So a perfect 1 basically means that there is no overlap whatsoever or no potential overlap in your clusters. And a score of -1 means that your data is effectively all overlapping. That's just some intuition around the silhouette score. We'll go through actually using it to determine our cluster amount in a second. So what I want to do is modify our code that we used to determine K, or that we are using to determine K. How I'm going to modify this is I will add a new list called, let's say, silhouette scores, silhouette, plural, and make this an empty list. Then in our loop over here, where we're trying out different values of K, I want to capture the silhouette score. What I need to do first is actually capture the cluster labels that I have. So cluster labels equals KMeans.fitPredict. This will give us cluster numbers each time we run the KMeans algorithm and run this fitPredict on top of our scaled data. Then I need to compute the silhouette score. So let's call this sil score here. And I'm going to use the function that I imported earlier of silhouette score from the scikit-learn library. So they've actually got a metric for this already. So they've captured this equation, the equation that we discussed earlier, already in the library itself. So we're going to leverage that. And to do that, we will take our scaled data df over here and then compare it with cluster labels to compute the silhouette score. And then I will just append this. So I'm going to say silhouette scores, our list dot append our sil score. We're just going to modify our plotting code so that we get a plot for the various values of inertia for our different values of K and our silhouette score for different values of K. So just added a extra subplot here, or I've made these subplots. So the first subplot is our inertia plot and the second subplot is our silhouette score subplot. Let's go ahead and run this. And in our visual, we get our same inertia plot over here, seeing that the inertia drops off the most at about 4 and 5. But if we look over at the silhouette scores, we can see that the 4 clustering, or K equals 4, has a slightly higher silhouette score than K equals 5 over here. So as the tiebreaker, I'm going to leverage the fact that the 4 cluster option has a slightly better silhouette score than the 5 cluster option, meaning that 4 clusters will have less potential overlap than the 5 cluster option. So we'll go ahead and use 4. Generally speaking, using less clusters is better, using the minimum amount of clusters, because it reduces the complexity of your further analysis. Imagine needing to deal with like 15 clusters or something like that. You then have 15 new data sets to interpret. So you do want to minimize how many clusters you make, or strike a balance between a huge amount of clusters and having no clusters at all. Let's go ahead and create our final model. And we'll just call this KMeans equals KMeans, again, with n clusters set to 4, the random state set to 42 again, and the max iteration set to 1000 over here. Then we can get our cluster labels, KMeans.fitPredict on our scaled data, or scaled data df over here. And then just to print out what the cluster labels look like, if I run this, I get an array with various numbers attached to the array, and these numbers represent the different clusters we got. Now I want to add these cluster labels to our original data. So we were using the non-outliers data frame, and I want to create a new column in the non-outliers data frame called, let's say, cluster, and assign that the value of the cluster labels. So let's go ahead and print out our results to see what that looks like. This is just complaining about me using a copy of a slice of a data frame. I'm okay with this. Nothing too bad to worry about there. But if we look at our data frame, we can see that we get our various cluster labels for our different data points. So for each customer, based on their monetary value, frequency, and recency features, we get a cluster assignment. Now that we have our cluster labels, what I want to do is actually visualize our data with the cluster labels added. So putting various colors on top of our data to see what the clusters look like in the 3 dimensions. So I'm just going to use our 3D plotting code and modify it a little to look at the different clusters, but I'll take you through that. So the plotting code that I'm going to be using is the same as before, very similar to before, with the addition of this dictionary over here, which is effectively a map between our cluster numbers, so 0 through to 3 for our 4 different clusters. And I've assigned different color values to each of these. I just chose these colors because they're quite distinct from one another. And what we need to do is create a map. So this variable over here, colors, takes the cluster value and maps onto it the cluster colors. We then use colors over here as an argument in our scatter plot. So C equals colors. Well, over here, this uses the mapped solid colors to color the different data points according to the cluster value. Let us run this and take a look at our plot. And we get a plot of our various clusters on top of our data. And this looks pretty good. I mean, this red cluster over here look like high frequency, low recency, and high monetary values. This blue cluster is more of a mid-range. This green cluster over here is lower monetary value, lower frequency, lower recency, so recently purchased at a low frequency and a low monetary value. And then this higher cluster over here is a higher recency, which means it's been a while since a customer has made a purchase. If they belong to this cluster, they're lower monetary value and of kind of average frequency. The next step we need to take is actually interpreting our clusters a bit more rigorously. It's great to be able to see the various values of the clusters plotted on the data, but we want to get a bit more specific in our analysis of each cluster. For that, I'm going to use a violin plot to take a look at the various distributions across the features. I'll take you through that in a second. The code that I've added here is to create our violin plots. I'll take you through each of the steps. And what we've done over here is just started in the usual way with a figure from matplotlib. And then I've added subplots, each subplot for each feature effectively over here. And these are going to be different violin plots across the different features separated by cluster. It'll become clearer when we go through the actual visual. So the first plot over here is using the Seaborn library, so sns.violinplot, and I want to use the x value of cluster. So on the x-axis, use the cluster number. On the y-axis, I'm going to plot monetary value in this case. And then for the palette over here, the different colors that I want to use to differentiate between the plots is the same cluster colors that we set before. And this hue variable just is set to allocate the cluster colors to the right cluster. It's a little weird, but Seaborn doesn't use color maps. Instead, it uses this palette and hue together. So just a little subtlety there. The next line over here is another violin plot, but I am plotting the full set of data without clustering. We're going to use this for reference. So it is purely a violin plot of the monetary value in this case, and I'm going to leave this in gray and give it a title of monetary value by cluster and a Y label of monetary value over here. I've just repeated this for each of our features, so monetary value, frequency, and recency. So same kind of idea across the different features. So running this, you'll see these kinds of plots over here. Now, these are called violin plots because supposedly they look like violins, but in my opinion, they kind of look more like stingrays, and stingray plot would be a lot cooler sounding, but oh well, we stick with violin. The violin plot is effectively just a box and whisker plot, so much like we had before, our box plots. They are captured in the center of the violins over here, and these violins just represent the distribution of the data, the frequency distribution of the data mirrored across the vertical axis over here. So these are pretty useful and convey a lot of information. They've got the usual information we get from our box plot plus the distribution of the data. And plotting this out, I've done this per feature. So this is for monetary value, and we can see the various clusters over here compared to this gray item over here, or gray violin plot over here, which is our full set of data without clustering. So we can use that for reference. I've done this for each of the different features over here, and you can see we get some kind of weird looking distributions as well. Awesome. So using this information, we want to come up with meaningful names for our clusters. It's great that we have these clusters, but the labels of 0, 1, 2, 3 are not very meaningful. And we want to interpret what the clusters represent and give them a meaningful and actionable name so that can be used by an analyst or someone looking at our results to actually take action on our insights. So the way to do this is to basically look at the different clusters across the features. And just going through this first example, on monetary value, this blue cluster over here, or cluster 0, looks like it has higher than usual monetary value. Its frequency is also higher than usual, and its recency is lower than usual, with the distributions looking pretty well centered, meaning that the data isn't too variable or there isn't too much variance in the data, which is a good thing because we can then generalize our analysis across the data. So for cluster 0, I'm going to basically do a little write-up of our findings. For cluster 0, our blue cluster over here, I've given a name of retain. So I'm labeling this cluster as the retain cluster of clients. And the reason is that this represents high value customers who purchase regularly, but not very recently. So the recency is kind of average. It's not stand out compared to the frequency and monetary values. So the focus should be on retention efforts to maintain their loyalty and spending levels, and then just give an action over here. You could do something like implement a loyalty program, personalize offers, and have regular engagement, like send them emails or that kind of thing to keep your business top of mind of the customer. So this is the type of analysis you want to do per cluster. I'm going to do exactly that. I'll skip through that, but effectively you'll want to go through cluster by cluster, really look at the results. So compare per feature, what does this look like compared to the full set of data without clustering, and make your analysis or make your recommendations effectively. All right, I've come up with rationales for each of our different clusters. So cluster 1 in orange, I'm calling re-engage. They have lower value infrequent buyers who haven't purchased recently, so we should try and re-engage them and try and re-spark that relationship between the customer and the business, called cluster 2 nurture and cluster 3 reward. You can go through my exact rationales. I'm not going to walk through that in detail, but in summary, we have our 4 different clusters with actionable names. So blue should be retained, orange should be re-engaged, the green cluster should be nurtured, and the red cluster should be rewarded. This is somewhat subjective, but really this is the result of our analysis and work. Someone may look at the same data and come up with a slightly different conclusion, but this is where the value of clustering comes in. You could discuss this with the business to see if their understanding matches your understanding of the actions that you should take or your rationales, but it's important to have this noted so that someone can look at your analysis and interpret it quite easily. If you're following along with this analysis, why not take a look at these plots and see if you agree with my rationale? Let me know in the comments if you have a differing opinion of my different rationales for the clusters. Now we've dealt with our main set of data, or our non-outlier data. It's important for us to remember that we actually have those outliers, the monetary value and frequency outliers, and we need to include those in our analysis as well. So that is the next step that I'm going to take. Now, if you remember, our monetary outliers over here and our frequency outliers over here, these 2 data frames represented our different outliers that we found in monetary value and frequency respectively. And if you remember, there was some overlap between the 2 in that some of the monetary value outliers could also be frequency outliers as well. So we want to take that into account. So what I'm going to do is basically form 3 new clusters, effectively the pure monetary outliers, the pure frequency outliers, and then the outliers that are both monetary and frequency outliers. So these are going to be three kind of manual clusters that we'll use to categorize our customers. To deal with their overlap, I'm going to first create a variable called overlap indexes, or overlap indices is probably the correct term to use. And we can just take monetary outliers df.index.intersection. So this will find the overlapping points between monetary outliers index and the index of frequency outliers .index. So this just gives us a set of indexes which overlap, basically indexes that appear in both of these outlier data frames. Then we need to go ahead and create each of our data frames for each of the different types of cluster that we're talking about here, or outlier cluster that we're talking about. So we can say something like monetary only outliers, and we can then go ahead and say monetary outliers df.drop. We want to get rid of the overlap indices, so this gives us only our monetary value outliers in this guy. And then we can repeat similar steps for frequency, and then include the monetary and frequency outliers as well. For the monetary and frequency outliers, I'm just taking the overlap indices, or filtering for where the overlap indices are present in the monetary outliers df. This is because we have our monetary outliers intersecting with frequency outliers, and that should give us the monetary and frequency outliers. Now we want to manually assign cluster labels to each of these manual clusters. So if we take our monetary only outliers and say cluster, so creating a new column called cluster, I'm going to give this a cluster value of -1. The reason I'm using a negative label here is just as a marker to say that we did this manually and this is not a result of the K-means clustering. I've repeated similar steps for the frequency only outliers and the monetary and frequency outliers, just assign them cluster labels of -2 and -3 respectively. Now I can take our 3 different outlier clusters over here, and I'm going to union them together into one data frame called outlier clusters. So outlier clusters df equals pd.concat. So concat will help us stack the data one on top of each other. So each of these data frames, I'm just going to union them together. And we do that by giving concat a list. So we will say monetary outliers df, monetary only outliers, frequency only outliers, and finally monetary and frequency outliers all together. And if we print out our result, outlier clusters df, we get our customer ID, the features, monetary value, frequency, and recency, and our cluster labels over here, our assigned cluster labels. Now I'm going to go through a similar exercise to what we did before with our violin plots, but specifically on the outlier data. This plotting code is really similar to what we had before. I've just defined a new color map for our new clusters over here and made the labels accordingly, so -1, -2, and -3, and then done our violin plots in the same way as we did before. So if we run this, we get our violin plots for our outliers. These may be a little harder to interpret, especially like this one over here with the monetary value being really low on the scale over here. But that's okay. We also have our information around like what type of outlier they are and use that to inform our analysis. So I'm just going to repeat the kind of analysis step that we did before to give these clusters meaningful names that an analyst can take action on. All right, so going through the analysis, I've given meaningful names to each of our outlier clusters. So for the monetary outliers, I'm going to call this the pamper cluster. They're high spenders, but not necessarily frequent buyers. Their purchases are large, but infrequent. The potential strategy is to focus on maintaining their loyalty, right? So basically take care of them. The frequency outlier should be upsold because they purchase very often, but not for very high amounts. So they should be upsold on new products. You could use stuff like loyalty programs or bundle deals to encourage higher spending. And then lastly, the monetary and frequency outliers should be delighted. They'll be called the delight cluster over here. They're the most valuable outliers, or our most valuable clients. And they have extreme spending and frequent purchases. So you should have like a VIP program to really convince them to keep buying from the business. All right, with our analysis done, we can move on to actually adding these labels to our data, so it is clear what each cluster represents in our data. To do that, I'm just going to create a dictionary of cluster labels and effectively take each of our initial cluster labels, the numbers, and map those to the actionable names we've given our clusters. All right, so that is our mapping done. Before we apply our mapping, we want to basically union our non-outliers and outliers data frames so that we get a full set of data with all the cluster labels applied. So I'm going to call this full clustering df equals pd.concat, so another union. And what we want to union is our non-outliers df and our outliers df, or outlier clusters df over here, to get our full set of data back. So let's go ahead and look at that. So this is just a mixture of our KMeans clusters and our manual outlier clusters as well. Now I simply want to add our cluster labels to each of our clusters over here. So the meaningful names that we created over here for each of the clusters, just to map them onto this data frame so it is clear what each cluster represents, or the cluster that each customer belongs to. To do that, I'm going to take full clustering df that we've created, add a column called cluster label, take full clustering df over there, and take the cluster and map that according to our cluster labels over here, and print out full clustering df. So all we've done is mapped these numbers to the meaningful names for the cluster. So for example, this customer 12346 is a re-engage customer, or our recommendation is to re-engage this customer. The very last step we want to take is to visualize our results in a single visual to summarize all of our findings. So we want to take our clusters with their unique labels, look at the volume of clients or customers in those clusters, and represent the features like recency, frequency, and monetary value of each of the customers. So I'm going to add some plotting code to do exactly that, and I'll take you through it. For our visualization, I will walk you through this somewhat complicated plotting code. The first thing I have over here is the cluster counts. So we want to look at the volume per cluster. So this is just taking the value counts per cluster label. So for each of these labels, get me the count of records in that particular cluster. Then I want the average values of each of my features. So I'm going to group by cluster label and take the mean of our recency, frequency, and monetary value. So use .mean over here to get their average. Then I'm going to do a bar plot for our clusters. So each of our clusters are going to be plotted against their counts, so their volume of how many customers are in each of those clusters. I'm using a palette over here, so this is a bit easier than manually assigning colors. There are a lot of preset palettes that you can use that make your visuals look quite nice. In this case, I'm using Viridis. Then I'm just setting a Y label and title over here. Then to add a secondary axis, I'm using this twin X or Twinks, which is a pretty funny way of saying that. So the axis over here is being mirrored, right? So we're creating a secondary axis to represent another value on the y-axis. So on one side, I want the counts or volume, and on the other side, I want the averages to represent that data as well, which is why I have two axes over here. Then I'm adding a line plot over here to represent the feature means. I'm using a set2 palette. This is just another palette available in Seaborn, and giving that a label. All right, let's plot this out to see what it looks like. All right, and you can see this visual really summarizes all of our findings. we have different bars representing each of our different clusters over here and showing how many customers fall into that cluster. So for example, nurture is quite big over here, meaning that this is probably the highest value actionable item we can take out of here, that you really need to start nurturing these customers. And this is the biggest grouping of customers that you have. On the line graph, I have the average value of each of our features. So we've got a legend over here to tell us recency is in green, frequency is in orange, and monetary value is in this light blue color. One thing that I'm not happy about is that the monetary value is quite high over here, or its average value is quite high compared to the rest of the clusters. So you can see this delight cluster over here has an insanely high monetary value, and that's squishing all of our other features. So it's really hard to tell the difference between like frequency and recency for these clusters over here. So what I'm actually going to do is divide the monetary value, or scale the monetary value by, let's say, like an order of something like 100 or something like that, just to bring this down but keep the shape of the data. So to do that, I'm going to add a new column to our full clustering data frame right here. I'm going to call it monetary value per 100. Actually, I want to give this a more explicit name. So let's say monetary value per 100 pounds. So it's clear what is being represented over here when we look at it on the visual. And we'll take our full clustering df, monetary value, and basically divide that by about 100 and see what that looks like. And in my code over here, when I do my group by, I don't want to group by monetary value. Instead, I want to, or aggregate monetary value, I want to aggregate monetary value per 100 pounds instead. All right, that should work. Let's go ahead and run this. All right, and that's a lot more clear. You can actually see after scaling that recency is doing something similar, but the shape of our feature means is a lot more clear after scaling back the monetary value. And in our legend here, it's clear to say that we're taking monetary value per 100 pounds. So we're dividing by 100 pounds, or dividing by 100 to scale back that value. And it's a lot more clear to see the shape of our features over here. And this visual is a lot more informing. All right, that was a lot of work, but a lot of fun to put together that project. If you've made it this far, thank you so much for watching and sticking around. I really hope that you found this valuable. So just to summarize what we've done, we explored and cleaned our data to prep for feature engineering. Then in our feature engineering, we created the features of recency, frequency, and monetary value. So we could then apply K-means clustering and uncover groupings in our customer data. And then finally, we summarized our data and findings in a visual to represent the results and drive actions from the business. If you have any questions or comments, let me know in the comment section below. I'd love to hear from you. If you found this video useful, just a reminder to give it a like and consider subscribing to the channel for more insights into data engineering, data science, and data analysis. And really the next step for a project like this is to operationalize this process or automate it. What happens when we get a new set of customer data? How do we repeat this process or automate the repetition of this process of clustering? I'll create a video on that soon and link to it here once that's done. But in the meantime, if you enjoyed this video, I think that you'll really enjoy my playlist of videos on data analysis, data engineering, and data science. Once again, thank you so much for watching, and I'll see you soon.